Okay, welcome everybody. It is a pleasure to introduce today Ali Khezeli from Inria de Paris and Tarbiat Modares University of Tehran. So today we are continuing the session in probability and statistical mechanics, and the topic of his contribution is unimodular continuum spaces. So please, Ali, go ahead.
Thank you very much for attending this session and for inviting me to these seminars. So I will talk about unimodular continuum spaces, or more precisely, unimodular random measured metric spaces. And I'm sorry for the error in the title of the seminar in the cover page. I just corrected it by pen. In the first part of the talk, I will say about mass transport principle in various subjects and how we are seeking for a common generalization. This includes mass transport principle in stationary point processes, in unimodular random graphs, and in unimodular discrete spaces, stationary random measures, and even in scaling limits of graphs. And also there is a mass transport principle in the topic of Borel equivalence relations, which I will mention if I have enough time. And I was looking for a common generalization of these mass transport principle. If you are familiar with at least one of these topics in the mass transport principle, if in at least one of these topics, then it would you can find the connection between the other topics here. First, I start with point processes. A stationary point process is a random subset of RD, or a point process in RD, such that if we translate it by a vector, here, if we translate it by a vector, then it has the same distribution as the original point process. For stationary point processes, we can define the palm version, or the palm distribution, which means that we condition that 0 is a point in the point process. This happens generally with zero probability, so there are we need some tools to define this conditioning. And one more heuristic is to see the point process from one of its typical points. This is also a heuristic, and a precise formula for defining it is this formula. If we want to define the average of some quantity h at the typical point, here phi0 is the palm version and phi is the stationary version. The average of a quantity h on the palm version is equal to the right-hand side. In the right-hand side, we have phi minus x, and x belongs to the unit cube, the points of phi in the unit cube, which heuristically means that we choose one of the points in this cube randomly with a uniform distribution, but in fact, we should bias the probability measure to make it more precise. This is the formula for defining the palm version. And we have a heuristic for this palm version. The heuristic is that whenever we want to do a summation over the points of the point process, this summation is generally infinite. But another replacement for that is consider the expectation of the same quantity at the root in the palm version. To be more precise, the expectation of G in the palm version is a replacement for the average of that quantity over all of the vertices. This is a heuristic which is useful when thinking on stationarity and the mass transport principle. We will see how this heuristic helps to imagine the formulas. For stationary point processes, we have some Mecke formula. I have written it in the top part of this page, but we can forget it and rewrite the Mecke's formula in the last line. The Mecke's formula says that if you have a quantity g here, g is a function that has as input a point process and 2 points. If you have such a function and we regard it as the message that x sends to y, or the mass that x sends to y, then here is the mass that goes out of the origin, and here is the mass that comes into the origin. And the mass transport principle says that the expected value of these two are equal. So the expected outgoing mass to the origin is equal to the expected incoming mass to the origin. This form is not typically known in the context of point processes. They usually use the first formulation in the top part, but the second one is closer to the mass transfer principle in other topics. Now, in unimodular graphs, we have also a mass transport principle. Actually, it's the definition of unimodular graphs. Here we look at the space of all rooted graphs, G and O, where the root is a vertex of the graph. When we consider a random element like this, we denote it by bold G and O. We call this random rooted graph unimodular if it satisfies this mass transport principle. Here, G is a function that as input has a graph and two vertices. Similarly to the previous formula, here is the outgoing mass from the origin, and here is the incoming mass to the origin. And the condition is that the expected outgoing mass should be equal to the expected incoming mass. I can write it this way. The expected of the outgoing mass should be equal to the expected incoming mass to the origin. I can rewrite this formula this way. An example is that if we have a finite graph and we choose the root uniformly at random here, then it would be unimodular. The reason is that when we choose the root uniformly at random, we can replace this expectation with a summation over all points. Here we replace this with a summation over all points again, and this would be just interchange of the two sums. So the mass transport principle is basically the double counting formula for finite sets or finite graphs. Another example is Khezeli graphs. Here there is no randomness, but anyway, this mass transport principle holds. The two sides are equal, and this is a connection between unimodular graphs and group theory. And also, if we consider any graph on a point process equivariantly, equivariant means that the construction should be translation invariant and some measurability condition, then this graph is unimodular. So any graph considered on a point process is unimodular, but the point is that we should consider the palm version of it, and we look at the graph from a typical point and put the root there. Then this rooted graph is unimodular. The reason for this claim is that the two mass transport principles look like each other, and when we construct a graph, this formula is transported to that formula. So in a lot of papers, these two different subjects have been studied, and also a connection between them have been studied. Some ideas are transported from one topic to the other topic, but we were thinking of finding a common generalization of these two topics so that we can justify why we have similar properties in these two theories. In one of my papers with some colleagues, François Baccelli and Mir Omid Haji Mirsadeghi, we defined unimodular discrete spaces. Basically, the random objects are a random discrete metric space with a root. And for once we define such a random object, then we can write the mass transport principle and give a name to it to call it unimodular graphs. Our motivation was that we were going to define a notion of dimension both for point processes and for graphs. So we defined this, and we defined the dimension for unimodular discrete spaces, which works for in both theories. So we can think of this as a unification of unimodular graphs and point processes, to be precise, palm version of stationary point processes, and also point stationary point processes. I said that palm versions of point processes have the mass transport principle satisfied, but this does not characterize all palm versions. There are some other point processes which have this mass transport principle, which are called point stationary point processes defined by Thorison and also developed by Thorison and Last. Maybe I'm wrong, maybe it's defined by both of them, I'm not sure. The next topic is random measures. In stationary random measures, we have a similar property. Let's define it. Phi is a random measure. So the heuristic is that we choose a measure on RD and we use randomness for choosing this measure. This would be a random measure. The condition is that if we translate the measure by a fixed vector, then it has the same distribution as itself. For stationary random measures, we can define the Palm version similarly, looking at the typical point chosen from that measure heuristically. And we have the same heuristic, and that the expected of a quantity at the root is a replacement of the average of that quantity over all points with that measure. This is just a heuristic. And we have a mass transport principle for random measures. This looks like the previous one. In the previous mass transport, we had a summation here over the points. Here we replace the summation with an integration. This looks very similar to the previous mass transport principles and creates a lot of connections between these topics, but still we have no unification of this mass, because this is a continuum version and the previous one is a discrete version of the mass transport principle. So one of our goals is to unify these discrete mass transport principles and these continuum mass transport principles. And there is another continuum mass transport principle in the next slide. Or let me say that this mass transport principle characterizes mass stationary random measures. This is more general than Palm version of stationary point processes. The next topic that we are going to unify is scaling limits of finite graphs. More precisely, we want to unify the mass transport principle in all of these theories. We are not unifying all of the theories, just we are looking at the mass transport principle. By scaling limit, I mean that we have a random triple Gn, On, and mu_n. Gn is a finite graph or metric space, which can be random or deterministic. On is a random point of or a random vertex of Gn with a uniform distribution. And mu_n is the counting measure on the vertices. The counting measure, I mean, if there are n vertices, put weight 1 over n over all of the vertices. This is a measure on the vertex set, a discrete measure. And now we want to scale the graph distance by factor epsilon n. So this is a new metric space, and scale the measure by factor delta n. We assume that in this sequence, this random triple, the distribution of this random triple converges. And the convergence means in the so-called Gromov-Hausdorff-Prokhorov metric. I don't want to emphasize on it, but the object that appears in the limit is a random metric space with a root and with a measure on it. This is the object, and there is a notion of convergence which is similar to the local weak convergence of graphs or the weight convergence of measures. These are similar to the Gromov-Hausdorff-Prokhorov convergence. And we will see that for these kind of scaling limits, the limiting space satisfies the mass transport principle. Examples is that if we scale the lattice ZD, we zoom out from it and look it from far away, we see RD, and the measure on RD is the Lebesgue measure here. If we consider the discrete measure on ZD and look at it from far away, we will see the Lebesgue measure if we scale it properly. Another example, which is the first probabilistic example of scaling limits, is the Brownian continuum random tree introduced by Aldous. He proved that if we scale a random tree with n vertices chosen with uniform distribution, then the scaling limit exists, and it is an important object in this topic. Another example Another example is, for example, the zero set of the simple random walk. It's a subset of Z, or it's a subset of Z, which is random. If you scale it properly, since the random walk converges to the Brownian motion, the zero set of random walk scales to the zero set of the Brownian motion. And this random set, which is the zero set, satisfies some mass transfer principle, we will see. And another example is Cayley graphs. We know that Cayley graphs are unimodular. The scaling limit of Cayley graphs has been studied by Gromov. Actually, this is the first study of scaling limits outside probability, which dates even earlier than Aldous, or almost the same time. This scaling limit, Gromov has used it to prove some group theory results, but it will be a locally compact group, and we will see that locally compact groups are also satisfy the mass transfer principle. Okay, so here we have two goals. One of them that I said is the unification of this mass transfer principle, and the other goal is to define, to develop the Palm theory on unimodular spaces. So here I mean that we have a random metric space, and we have another point process on it. Then we want to develop the Palm theory for this two-layer randomness. Here, the Euclidean space is replaced by a random metric space, and then a point process on the Euclidean space is replaced by a point process on another space, and we want to develop the Palm theory on it. This is useful, for example, if we want to consider point processes on these scaling limits or random surfaces and things like that. This will be useful for this topic. Okay, so now I want to define this unification, which is unimodular continuum spaces. First, what is the space, the probability space that we study? This is the space of all triples X, O, and mu. Here, X is a metric space, O is a point, and mu is a measure on X. We have some conditions where X should be boundedly compact, which means that every ball should be compact. Every ball with finite radius should be compact, and the measure should be boundedly finite, which means that every ball should have finite measure. These are the conditions. There is some metric on this space M star, which makes it a Polish space. This is the Gromov-Hausdorff metric that I just mentioned. Now we consider a random element of this M star. I'm more comfortable to denote this random element by a bold triple X, O, mu. But we should keep in mind that this triple is one object, which is a random element of M star. We cannot separate X from O. They don't live separate, they live together. Usually for random elements, we use one symbol, but I'm more comfortable with this because when I prefer to write the expected value of F in this form instead of writing it as an integral in this form. So the left side is more intuitive for me to the right side. Now I define unimodularity. We say that this random measured metric space is unimodular if it satisfies this mass transport principle. Here we have a function that g of O and X is the mass that O sends to X. Of course, the mass depends on X and mu as well, capital X and mu as well. So if you have such a function, then the expected outgoing mass from the root should be equal to the expected incoming mass to the root. Note that the outgoing mass is the integral with the measure mu, which is in the definition. Mu is the same measure which is in the random triple. Here we have no counting measure. For discrete spaces, we have a natural measure, which is the counting measure. There is no counting measure here for general metric spaces, so we include it in the definition. So it's we have a choice of which measure to choose in the definition here. So maybe we can have a space X, O, and various kinds of measures on it, and they are unimodular. We can write it in this form. The expected outgoing mass is equal to the expected incoming mass. So the definition is very simple. The only complication might be in the topology and the GHP metric, which I had to spend 1 or 2 papers for this purpose. I have 2 papers on the GHP metric. One of them is needed for this consideration. I actually found that this had been defined by Louis Bowen in 2015. I was not aware of his definition, but Louis Bowen only gave the definition and gave some basic examples. So he did not develop a theory and study the properties of unimodular continuum spaces. Sorry, I lost my connection. Do you see my screen now? I don't know why Zoom was.
No, the screen interrupted.
Sorry, my Zoom is closed. I'm trying to reconnect. I'm sorry for the problem.
It's okay. Can happen.
Okay, I'm back. So let's give some trivial examples. A trivial example is when mu is the 0 measure. So both integrals in this formula will be 0. So this is not interesting. The other example is that mu is the Dirac measure at the root. In this case, both integrals are equal to the expectation of g of O and O, which are equal. This is also not an interesting example. Another example is when the space is compact and consequently mu is a finite measure. In this case, we can choose O with the measure mu exactly. So mu is a finite measure. We can normalize it to find the priority measure and choose a random root with distribution proportional to mu. Then this would be unimodular. This is a generalization of the random graphs with a uniform random root, which are unimodular graphs. For these models, we have a rerouting invariance property, which means that if we have unimodular compact space and we reroute the space randomly, we choose a new root with distribution proportional to mu, then it has the same distribution as the previous one. This is known in some examples of scaling limits. For example, in the Brownian continuum random tree, it has been observed that it satisfies the rerouting invariance property, and in some other examples, but it was not expressed in terms of unimodularity. In general, the intuition, even in the non-compact case, is that the root is a typical point according to the measure mu, which means that the expectation of any quantity at the root is a replacement of the average of that quantity with the measure mu. Here, the measure is an infinite measure generally, but this is a heuristic. When we want to consider the average with measure mu, we replace it by considering the expectation at the root. Some more examples, which already discussed, are a palm version of point processes, random measures, unimodular graphs, and all of the previous topics that we have studied. They are special cases of this mass transport principle, but we should be careful because there are some more geometric structures. For example, in graphs, there are some edges and graph theoretic properties that might be not present in the more general setting. Or in point processes, there are some translations and there are some x-axis, y-axis. You have forgotten these extra structures. and we only look at the metric space that we have on the points. And this is we should keep in mind that we say that it's a common generalization, but with forgetting some geometric structures. Another example which I found recently is unimodular random manifolds. It's basically the same definition, but instead of a random metric space, we restrict attention to random manifolds with a fixed dimension. This is studied by Miklos, Abert, and Beringer. I have forgotten the first name. And they have developed a theory of unimodularity for random manifolds. So our work can be thought of as generalization of that work as well. So another example is weak limits. If you have a sequence of unimodular spaces and this sequence converges weakly, then the limit is also unimodular. Corollary is that all of the scaling limit examples are unimodular, but with the assumptions that I said. I said that here we have a finite graph or metric space, and the root is chosen with the uniform distribution on the finite space, and we consider the weak limit of this sequence. With this example, all of the scaling limits, with this assumption, all of the scaling limits are unimodular. So this is a common generalization of the scaling limits as well. And the corollary is that all of the compact scaling limits have the rerouting invariance property with the assumptions about the scaling limits that I mentioned. Another example is symmetric spaces like the Euclidean space. There is no randomness here. The Euclidean space with the Lebesgue measure is unimodular. We can remove the expectation in the formula of the mass transport principle. So basically, it says that the integral of g of 0 and x is equal to the integral of g of x and 0. This holds even without expectation, because we know that G is invariant under translations and under all isometries, in fact. G is invariant under translations, so these two quantities are equal. Not equal. In fact, the right side is equal to G of 0 and minus x. So the two integrals would be equal. We can generalize this to every unimodular topological group. This is a more generalization of RD. So every unimodular group is unimodular in this sense. Actually, the name of unimodularity comes from group theory, in fact. Another example is the hyperbolic plane with the natural volume measure. This is not a group, but it's unimodular. In fact, it's a symmetric space with such that the automorphism group is unimodular. So if you have any other symmetric space with a unimodular symmetric group, then it is unimodular. Another example, which there is still no randomness, is deterministic spaces. Assume we have a deterministic space X and mu, but we want to choose the root randomly to make it unimodular. It need not be symmetric, but in some other examples, we can choose a random root to make it unimodular, like the canopy tree, if you're familiar with it. It's a deterministic graph, but we choose the root randomly to make it unimodular. Or in quasi-transitive graphs, we have finitely many layers. We need a lot of automorphisms to divide the vertex set or the points in orbits and choose a random point according to this orbit structure. In my paper, I have written some necessary and sufficient condition for this in terms of the automorphism group. It will be technical to include it here, but it characterizes all deterministic spaces. An example is the horoball in the hyperbolic plane. If you consider a horoball like this, which is tangent to the boundary of the hyperbolic space, then on this horoball, we can find a random point to make the horoball unimodular. the idea is that if you consider parallel horoballs like this, then these horoballs, when we move towards this ideal point, the horoballs shrink exponentially, and it behaves like the canopy tree, a continuum version of the canopy tree. We can choose the root, for example, on this line with an exponential distribution, then it will make it unimodular. This is an example of the application of this theorem. I'm sorry that I'm going very fast. I hope that there is no problem. If there is any question, please ask me. Now I give some properties of unimodular spaces. One is subset selection, which generalizes a similar property in unimodular graphs. Assume that we select a random subset of the space. So we have a unimodular space, X, and we select a random subset of it, but the random subset should be defined equivariantly. We call it equivariant, which means that we should not look at the root. To be more precise here, to every to every pair X and mu without root, we assign a subset of it, and assume that this function S has some good properties, which one is automorphism, isometry invariance, and the other subset is some measurability condition. We call this a factor subset. If we have a factor subset and the space is unimodular, we have this property that the root is in the subset almost surely, if and only if the subset has full measure, almost surely. Another way to say this is that the root is in the subset with positive probability, if and only if the subset has positive mass with positive probability. So this is an evidence for this typical point argument. The root is a typical point. So if a typical point is in S almost surely, it means that the subset should be a full measure. The subset need not be the full S, full X, but for example, could be the support of S, for example. If a typical point is in S with positive probability, which means that S should have positive mass. This is the heuristic. And the corollary is that O should be in the support of mu almost surely, because it has this property. So the support has full mass, therefore it should contain the root according to this lemma. Another property is root change property. So I now define what it means to change the root. Assume we have a unimodular graph. By changing the root, I mean that for every deterministic triple, X, O, and mu, which is different from the random one, for every deterministic triple, we consider a probability measure on X. This probability measure determines where to jump, where to change the root. Now we choose a new root with this given distribution, and we call it a root change. This rule for root change. This alpha is a function, say that describes the rule for changing the root. It should have some good properties like isometry, invariance, and measurability. And the question is, when we have this property that after root change we have the same distribution. The general condition is that if you look at this root change, if you look at this alpha as a Markovian kernel on X, because for every O, every point O, we have a probability measure. This can be regarded as a Markovian kernel. If this Markovian kernel preserves this infinite measure mu, then we have this property. So this is it's still not necessary, but a very good property. Usually this happens in all of the examples, except in some special examples, that mu should be a stationary measure for this Markovian kernel. Then after the root change, we will see the same distribution. This is the general lemma. This is a generalization of Mekke's point stationarity theorem. Mekes theorem says that if you have a bijective map on the point set from itself, from the point set to itself, and we change the root according to this map, then we preserve the probability measure. Note that changing the root by a bijective map, this bijective map preserves the counting measure because every point has exactly one inverse. So a bijective point map exactly preserves the counting measure. So it's a special case of this level. We have some generalizations here as well. If it does not preserve the measure, we have to bias it by something which is f minus here. If f is the density of alpha with respect to, I said that alpha is a measure on X, mu is also a measure. If it has a density, we call it f of O and X. Then in general, we should bias the probability measure by f minus of O, which is the incoming mass to O. In particular, if the density exists and f minus is equal to 1, then we preserve the probability measure. This is important in the next slide. So I fix such a function f, I call it h here, that has this property that h minus is 1. So both h plus should be equal to 1 and h minus should also be equal to 1 because we have here alpha was a probability measure. So the integral of the density is 1, which means that h plus should be equal to 1. And we need h minus equal to 1 as well. Such a function, maybe I haven't seen such a definition earlier, so I have defined it myself to create such a function h. This is very useful. We'll see in the next theorem to have a function h such that both h plus and h minus are equal to 1. There's a simple formula for defining such a function h. I have written it here. It's easy to verify that it satisfies this. The only assumption here is that in the denominator should be well defined here, which is h0 minus of z should be finite. So fix such a function h as here, and now we think of h as a rule to change the root. So we are at the origin now. We want to jump according to this h. More precisely, h is a function if we consider the distribution which has density h, which I call it h mu here. We choose the next point with this distribution. Now we have x1. From x1, we also jump to the next point x2, and also jump to the next point x3, and so on. There is a way to define it on negative values of n as well, and we will find a by infinite sequence on x. We call it a random walk on x with kernel h. And the point, the theorem is that this characterizes unimodularity. A random metric space, a random measured metric space is unimodular if and only if this random walk is stationary and reversible. Stationary means that if we move the root to x1, and shift the sequence as well, then we have the same distribution. And also if we reverse the sequence, the ordering of the sequence, we have the same distribution. This is a characterization of unimodularity. We have a similar property for the unimodular graphs, for characterizing unimodular graphs by the simple random walk. It's again stationary and reversible, but in that setting, we have to bias by the degree of the root, which is a little problematic because sometimes the expected degree is infinite. That characterization only holds for unimodular graphs with finite expected degree. Here we have no such assumption. By this simple trick, we can get rid of this finite expected degree condition in some of the theorems. Another result is ergodic decomposition. We can define ergodic unimodular random metric spaces. Let me go very fast here. Ergodicity means that every invariant event has probability 0 or 1. Invariant here means that events that are invariant by changing the root. I have written it in the second line. So we look at events that are invariant under root change, and the definition of ergodicity is that every invariant event has probability 0 or 1. We have two theorems. One is that this ergodicity condition is equivalent to the condition that the simple random walk is ergodic in the classical setting. There is some explanation here, so let me skip it. The other theorem is ergodic decomposition, that every unimodular random measured metric space the distribution can be written as a mixture of ergodic probability measures. So ergodic ones, as in classical or ergodic theory in other topics, the ergodic measures are the extreme points of the set of all unimodular measures, and every unimodular measure can be written as a mixture of the ergodic ones. Okay, now I go to the second part of my talk, which is palm theory. I want to consider a random triple plus one additional measure, which we call it phi. It's not very trivial to how to consider this as a probabilistic object. To get around this, I consider a random quadruple here. I assume that we have a random quadruple, which is a random element of this space M2 star, equipped with two measures. I call the first measure mu and the second measure phi. We assume that this random quadruple is unimodular, which means that we have the same mass transfer principle. The assumption is that the function g in the mass transfer principle can depend on this phi as well. This makes it different from the previous mass transfer principle. If we have such a quadruple, we say that phi is a random, phi is an equivariant random measure on X. This is by an abuse of notation. In fact, another equivalent definition is is given by this theorem. This theorem says that if you have this unimodularity, then we can consider the conditional distribution given the triple X, O, and mu. This conditional distribution has a version which does not depend on the root. This is analogous to stationarity. So we have a random object on the space, and the distribution of this new random object is translation invariant in some sense, which says that the distribution does not depend on the root. In either of these definitions, we say that phi is a random measure, an equivariant random measure on X, O, and mu. So we want to develop palm theory for these objects. An example is where phi is mu itself is equal to mu, or phi is any function of mu and any factor of X and mu. This is a trivial example. Another example is that if we have phi, then we can consider the intensity measure of phi. Here, recall that X and mu are deterministic, and phi is an additional random measure. It is defined by additional randomness, by extra randomness. So we can consider the expected value of phi, or we may think of it as the expected value of phi given X and mu. This is the intensity measure. The intensity measure is also an equivariant random measure, which of course has no extra randomness here. It's a factor measure. Another important example is the Poisson point process. We need a base measure. For example, we can choose the same measure in the definition. So we have a space X and mu. We use additional randomness to sample a Poisson point process with intensity measure mu. This is an example of an equivariant random measure, or an equivalent point process on X. To define palm, we note that there is no unit cube here. So the formula for defining the palm of a random measure does not work. Instead, we need other definitions. We can use Campbell measure and tessellation ideas from point process theory. So I start with tessellations. There is a theorem that if we can tessellate the Euclidean space such that every point of V is assigned to a tile, and all of the tiles have equal volume, I call it a fair tessellation. Then we can choose the tile that contains the origin. Here is the middle tile, and we change the root according to this formula. We choose the point of V that belongs to that tile, and we do this root change. By changing the by doing this root change, we find the palm version. This can be seen as a definition of palm as well, if we consider it such a tessellation. But such a tessellation is not easy to define, so that all tiles have equal volume. We can generalize it. Even we do not need a tessellation. We can assign tiles to every point of V. Tiles can overlap, can leave some place uncovered, and also do not necessarily have equal volume. If doing so, every point is covered more than once. For example, this point is covered in 3 tiles. We have a generalization. Instead of a tiling, assume that we have a function h of x and y such that h minus of every point is 1. H minus is the integral of h of x and y dx. Here in this picture, let h of this x and y here be 1/3, for example, for these 3 points. Then h minus of y would be equal to 1 because we sum 3 points, which the value of h is 1/3, so the sum is 1. More generally, if we fix such a function h, it's a replacement of tessellations. Then we can do the same root change. The theorem is that the palm is obtained by biasing the probability measure and then shifting the origin to a point of V chosen with distribution proportional to h. There is a formula to it. Let me draw it on the picture. Assume we have the root. For example, the root is here. And now the root is covered in 2 tiles. It's enough to move the root to one of the centers of these 2 tiles randomly. Here, this is exactly this formula. A point chosen with distribution proportional to h of 0 and c dot. We can generalize this formula to random measured methodic spaces. We will see. For unimodular spaces, again, we fix a function h such that h minus is equal to 1. It's easy to construct such a function. Now we do the same. We bias the probability measure and choose the root with distribution equal to h times phi. I mean, this is the kernel for changing the root. By this root change, we find the probability measure and we call it the palm distribution. This is the precise formula. I can skip discussing the elements of this formula, but the idea is similar to the root change of tessellations that I just mentioned. Here, it gives us both the definition of the intensity of the random measure and also the palm version of the random measure, the palm distribution. We have a property which is called the Campbell formula. Here, I denote by E0 the palm distribution, which means that we change the root to a typical point chosen with distribution phi. This is the intuition of the palm distribution. by an abuse of notation, I use the notation E0 for this new random object, which is obtained by the palm, which means that in this point, the root in this in the right hand side, the root is a typical point of phi. In the left hand side, the root is a typical point of mu. This is the difference. This is an abuse of notation because I have used O in both random objects, but I had no choice. It would be a lot of complications if I used a new notation for it. The Campbell formula says that if you consider the expected mass that goes out of the origin, here the mass that goes out of the origin is integrated with measure phi. Then this is equal to the expected mass that comes into the origin, but the incoming mass is integrated with measure mu. We have such a mass transfer principle, and there is a lambda here as well, the intensity. Sorry for this. There is a lambda here as well. The heuristic is that here the root is a typical point, so I can replace this expectation heuristically with integration d mu. Here the root is a typical point of phi. I can replace it with integration d phi. And it's a Fubini theorem, which we interchange the integrations. Some more properties of Palm is that if we consider the Palm version, and now we forget about mu and replace it by phi, this new random metric space is unimodular, random measured metric space. So X is the same, but the measure from mu is changed to phi. If we simply change the measure, it is not unimodular. But if you consider its Palm version, then the Palm version is unimodular. This generalizes the fact that Palm of stationary point processes is unimodular. So this generalizes that fact. Now do it again. Now here phi is the base space and mu is a random measure on this. We have interchanged the role of phi and mu here. We can do it once more to do this Palm of mu now. If we do it twice, we obtain we arrive to where we started. So here in the Palm version, now mu is a random measure because the base measure is phi here in this setting. We consider now the Palm of mu, then we will obtain the same, the original probability measure. So to say it in this way, Palm inversion is nothing more than doing one more Palm. So this is a unification of Palm inversion and Palm as well. Palm inversion was a problem in stochastic geometry. The problem is that when we define the Palm distribution, how can we recover or reverse the construction to obtain the stationary version? Now we see that this Palm inversion is nothing more than doing Palm again. In the point process setting, after we do the Palm, now the Lebesgue measure is a random measure on this new space. We consider the Palm of the Lebesgue measure and we obtain the stationary version. This is the idea. We have several examples of Palm. Let me just say the important ones. If we have the Poisson point process with intensity measure proportional to mu, then we have a similar property similar to Slivniak's theorem. The Palm of the Poisson point process is nothing more than inserting one point at the origin. Thus, heuristically, we want to condition that there is a point at the origin, and since it's Poisson, this conditioning does not affect the rest of the space. This is the same heuristic in point process setting. Another example is that many constructions in the theory of unimodular graphs add some structure to the graph and change the root to construct new examples of unimodular graphs. One is planar duals. We have a unimodular planar graph. We add something to it, which is the faces or the center of the faces. Now we make the dual graph unimodular. Here we see that this process is an example of PALM, because this counting measure of the dual graph can be regarded as an equivalent measure on the original graph. Now it's enough to consider the PALM of this counting measure of the faces. This PALM exactly gives this construction of the dual graph, this construction of making the dual graph unimodular. It's exactly an example of PALM. Or any other examples when in the literature where we add some graphs and structure to a graph and obtain a new unimodular graph, all of them are examples of PALM. I wanted to say an application of this PALM theory and also one definition. One is amenability. I just have time to state the theorem. I defined various notions of amenability for unimodular continuum spaces, which are based on existing definitions in other theories. One definition is by existence of a local mean. I have definitions in the next slide, but I don't have time to it. I just can say that for every bounded continuous function on X, we have to assign a mean in translation invariant way. We call it the existence of a local mean. This is a definition of amenability. The other definition is the existence of an approximate mean. Approximate mean means a function on X, which the integral is 1, but is very flat. And if you have a sequence of such functions that are flat and more flat with some condition, we can construct a local mean out of it. This is called approximate mean. Another condition is hyperfiniteness, which means that basically we can partition X into some finite parts, finite measure parts, but can be unbounded but have finite measures, and such that the element, for example, the element containing the root has a very small boundary. This is the heuristic. The other condition is Follner condition, which has almost the same heuristic. If you have a partition such that the cell of the origin has very small boundary, another formula to formalize this is called the Follner condition. And I proved that these conditions are equivalent. The proof method is that I consider the PALM, let me go to the proof method. I consider the Poisson point process on X and consider the PALM version of the Poisson point process. Using this PALM measure, I could construct a Borel equivalence relation, a countable Borel equivalence relation, and the PALM is an invariant measure for this Borel equivalence relation. And now using the theory of countable Borel equivalence relations, I could prove that all of the 4 definitions are equivalent to the classical definitions for this partition R, for this equivalence relation R. And we have a theorem for countable Borel equivalence relations that all of the definitions are equivalent. This is the way I used PALM theory to prove this amenability theorem. Okay, that's it. Thank you.
Thank you very much.
Thank you very much for this talk.
Thank you.
Thank you very much, Ali.
If there are any questions, I will be happy to discuss.
Yeah. So I have a question about the slide about fairness. When you mentioned fair tessellations.
Fair tessellation.
Yeah.
Yeah.
So just to see if I got it correctly. So in the case of, let's say, points on the surface of a sphere, this would correspond to the set of points that will flow towards the center of attraction with a potential of the kind like a logarithm of the distance. That's the
if I get it correctly, this is a way to define tessellation, which is the I think it's called gravitational allocation.
Yes. Okay.
This is a way to define the tessellation. Then the set of points that are attracted to that point is the tile of or the cell of that point.
I see. But you said that you can go beyond that. You can allow overlap between the different regions and.
Yes. In general, for other shapes like this, that we have some tiles that overlap and are not in the same volume, we can construct a palm using this structure as well. I use this idea to define.
Okay. Thanks.
Thank you.
Other questions?
It's not really a question because, okay, there is many technical things that I couldn't follow. But I was curious about the action. So you have the invariance. We can generalize to action of any group. So because you said some comments, but on previous slide.
It was in the example of deterministic spaces, I guess. Here. Here we have a deterministic space which has a lot of symmetries, or the automorphism group acts on it. And the action should be both isometry and measure preserving. This is our condition. Yes, more generally, we have an action of a group on a measured metric space, which is both isometry and measure preserving. And this gives, if the group is unimodular, then we have this property. The theorem says that under which conditions we can find a random group to make it unimodular.
I wonder if there is some
or maybe
Lie group involved in this theory. No, there is no.
No Lie group is not required. It's only required that we have a topological group which is unimodular, which means that every topological group which is locally finite has a Haar measure, has two Haar measures. One is left and right. If these right Haar measures are equal or have versions which are equal, this is called a unimodular group. This is we don't need to have the Lie construction. It will not be a manifold, for example.
Okay.
And an important example is the automorphism group of graphs. If you have a transitive graph, the automorphism group is a topological group, but I guess it's not a Lie group. But it fits into this assumption.
Okay. Okay, thank you very much.
Thank you, Aslan.
Are there any other questions? Okay, if not, let's thank again the speaker.
Thank you.
His contribution, and just remind that in 1 week we will resuming back with another session for this theme on probability and statistical mechanics. Thank you very much, Ali.
Thank you, everyone.
Thank you,
Have a
everyone.
good day.
Yes.